Hello viewers and welcome to another episode of Space Science with Python. Last time we had a small introduction into sky coordinates, especially the equatorial and the ecliptical coordinate system using Stellarium, the open source planetarium software that I showed a week ago. So in our first session about the planetarium software. And today we will finally use Python and Spice to perform some computations on our night sky. Now, we will not really cover today coordinates, more like distances between objects in the sky. And with distance, I don't mean the Euclidean distance, like the distance between the Earth and the Moon or the Earth and Venus, more like the angular distance, so the appearance in the sky, so the distance between Venus and Sun, the Sun and the Moon, and so on. And I was thinking, okay, how could I introduce this topic in an interesting way? And for this, I would like to show you Stellarium first. Now, this is now a little bit familiar for you, hopefully. Stellarium, the planetarium software, as you can see, it's now 5 p.m. here in Germany. And the sun sets currently, at least in my planetarium software. Outside it's quite cloudy. And when we move a little bit forward, we see that when the night starts, that Venus starts to appear, also Saturn and Jupiter. And Venus is it's our innermost, not the innermost, but a planet that is closer to the sun than ours. The closest planet is Mercury. And depending on the position of Venus and the Earth, Venus appears as the morning star or as an evening star. I know it's not a star, but this is like the saying, the common saying that there is a star in the morning hours or in the evening hours. And you can see currently it's the evening hours. So when we go a little bit further in time, let's use the date and time widget here and just increase the days. We see a certain movement of Venus over the next couple of days. We see also the moon moving, and the Venus appears, I wouldn't say steady state, but it's now not as moving as like Jupiter and Saturn at the same time here. Well, we will not cover the reason for this, but what we see here is something that is very interesting for astrophotographers. Or if you have some camera with a telelens, you maybe would like to take a photo of Moon and Venus. And of course, we can compute the coordinates, like the right ascension and declination, or the ecliptical coordinates, and see how it evolves over time. But that would be quite, I wouldn't say difficult. We will use a different technique a little bit. We could, for example, use our tool here, our planetarium tool, to see when are Venus and Moon quite close, to create a nice picture. So there are a lot of nice images outside, especially a nice setting is the Moon and Venus with some landscape, and then you have a very nice picture. Now, this is not really 100% scientific, I know, but we can use this case to get familiar with new SPICE functions and try to find out when we have some, let's call it photogenic hours or days where Venus and Moon are quite close to each other. Sounds a little bit foggy, but things will clear up in a moment. Now we can maybe turn off the atmosphere and the ground, track Venus and see how close actually the Moon gets. And you see, well, this is very close, Moon and Venus here. The Moon is almost covering Venus, and we have here another tool to determine the angular distance, and this is like less than a degree, and this is quite impressive. So for me in Germany, I think this will be below the ground, so I won't see it. But if you are lucky somewhere else on the planet, don't miss this chance on the 8th of November. So what we will do is we will try to compute the distance between the Moon and the Venus to determine when we can take nice pictures. But this is not the only value or measure we have to take into account. There's also a second measure, namely the distance between Venus and the Sun. Because at some point in the future, so when time goes on, Venus will move closer to the Sun again. And at some point, it's so close that we cannot really take a photo anymore. It's really just broad daylight, and it's quite difficult to determine or to create a picture with this in this setting. So if we just follow it a little bit and take also the moon into consideration, they're also quite close here. And I still have this thing running. And we turn on the ground and the atmosphere. Well, it's quite difficult to capture the Venus and the moon. So the requirement of an angular distance is not enough between Venus and moon. We have also to take the angular distance between the moon and the sun and Venus into account. Now again, this is a very simple case to get familiar, to warm up a little bit with sky coordinates and how things appear in the sky. And later we will talk a little bit more in detail about the movement and so on. So what do we have here? I prepared another folder, Planets in the Sky. The link is in the description. It's again on GitHub. And I prepared some scripts that may appear familiar from last time, where I just compute some initial time and convert it to ephemeris times, and have some initial and end time between I just had picked up the 1st October and the 1st October this year to the 1st June next year, with a certain delta in between, so at the ephemeris time in hours. And I have here now a pandas data frame. I just simply call it inner Sol system data frame. The first column is now the ephemeris time, and second column is the UTC to have also a human readable format. And now we have to compute the angular distance between the sun and the earth, as seen, the sun and the moon as seen from the earth, the sun and Venus as seen from the earth, and of course between Venus and moon. And so let's start with it. In our first, not first, but our next entry, we will call it, for example, Earth, Venus to Sun angle. So I think this is quite self-explanatory. We will compute everything in degrees, so we have to take this into account. And of course, I loaded already some important SPICE kernels that are in the kernel meta.txt. It didn't change compared to the last time, so it's I think should be quite also self-explanatory. And we use, of course, the ephemeris time to compute some state vectors or some positions. So we use the ephemeris time, and we apply for each row a function to compute the angle between Venus and Sun as seen from the Earth. And what is this function? Well, don't worry, I already prepared it. There is another function in SPICE called phase Q. And it says phase angle quantity between body centers. So the input is here. We have the ephemeris given in seconds past J2000. So this is what we have. This is our first column. We need a target body name. We need a body that's called, this illuminated, or we call it illuminating body name, and an observer. And now we say, okay, it's quite easy. The target is Venus, the illuminating body name, well, the sun, the observer is the Earth, right? Well, we have to take a look at the documentation. And I know this looks a little bit old, but it still works out, and it's quite easy to understand. So what is the phase angle? It's visualized here in this part in the center now. In our case, we are searching for an angle between the sun and Venus. And in our case, we can say, okay, the illumination is, we can take it the sun, this is fine. But the observer in our case is Venus, not the Earth. The Earth is the target. And that's how the name phase angle is defined, right? So it's not like really trivial to know what this angle is because it could also be the angle between the illumination, the vector from the illumination body to the observer and to the target. But no, here in space science and also in SPICE, the phase angle is defined between the observer and the illumination body, with the target as a center. So in our case, the target is the Earth. So we have to take this into account. Otherwise, we would get some messed up results. And another another input is the aberration correction flag. Now, what is this? Here's some explanation. There are some strings we can use as an input. The first one is none, which says don't apply any correction. And the other says, well, apply some one-way light time correction. So what does it mean? Well, if you want to compute the angle between Venus and Sun, you need to take into account that the light from Venus to Earth and from the Sun to Earth, it takes some time. So when we see, for example, let me just say some random number, the angular distance between Venus and Sun is 10 degrees, then while the light was traveling, the objects were already moving, and the angle is, let's say, not correct in the sense of what's the steady state of the solar system. I know time is relative and so on, but in our case, in the solar system, we can easily compute either the current steady state geometric vectors, or we can take into account the light time travel, the light travel time. And since we are observing from the Earth, we should take this into account. But I would also like to say that in our case, it's not really important, because whether the Sun is, or whether Venus has an angular distance to the Sun of 10 degrees or 10.001 degrees doesn't really matter. So we are talking just about a few minutes of light travel time, and the movement of the objects in the sky is quite small. You have to consider the light time correction, of course, if you want to, for example, communicate with a spacecraft, right? So the spacecraft is moving, you have an antenna pointing into the direction of the spacecraft. Then, of course, you have to point into the direction where the spacecraft will be in, like, let's say 15 minutes, because your spacecraft is already far, far away. Otherwise, you don't get any contact with it, and then, yeah, the mission is lost. Or you are wondering why you don't get any results or any communication with the spacecraft. But in our case, it doesn't really matter whether we take none or some light time correction. But yeah, for the sake of completion, let's also use the light time correction. Now, the phase EQ function will return the values in radians, so we have to convert them in degrees to get some nice degree number. So we apply spicy pi phase q, and we say that the ephemeris time is x, or from our lambda, because we are iterating over the ephemeris time column. Then we have the target. Remember, the target in our case is the Earth, and we need to apply the NIF IDs. So the ID list that represent the objects. So the Earth is 399. All other objects, I will provide a link into the description where you can see also the other numbers of other objects. The illumination body is the Sun. It's number 10. And the observer is Venus, and in this case it's 299. Now you would say, wait a second, 399, it's the body center of the Earth, but I'm not sitting on the body center. Well, that's right, of course. We are sitting, or you are sitting probably on another location, other longitude, latitude values on the Earth than I do. But let's keep this simple. Of course, you could also correct this considering the location, the geo coordinates, but this is something for a more advanced session in the future. And of course, we have the app core, and we take the light time correction. We apply it here. Now let's have a quick, let's see whether the code works. And this is now really, this is of course some kind of effect presenting things. I totally forgot to connect to the container. So I have to still open the container, but the container is built, so I don't have to interrupt the video, I think. Let's have a quick look. So this happens, and so you see that the container is now building up. Yep, perfect. So we can, now this is from last time, we can now open our script again. Apologize for this. This is like really live coding, I would say. Okay, I think the container is now open. Nice. So let's execute the code. Choose the kernel. Yeah, this works, and this works, and now let's see whether this works. No, there's an invalid syntax because I forgot a comma here, and now it works as well. We can have a quick look to see whether we get some results. Yeah, we get some angles, perfect. And now we can simply copy paste this and apply the same computation for the moon and also for so between moon and Venus and moon and sun. So let's change the values here first for Earth, moon to sun. Same logic, we apply the ephemeris time, and the target in our case is again the Earth. Illum is again the sun, and the observer in this case is the moon, and the moon has the ID 309. And then we have, of course, the next parameter, the moon to Venus. In this case, the target is again the Earth. This time we are not talking about the sun. This time it's like the it's Venus, and the observer is the moon. Yeah, I know the wording is a little bit confusing. Observer, target, illumination body, but it really doesn't matter if you check the logic of the phase Q function. It's simply computing this phase angle, and they had to name it somehow, right? The point is why it's called target, observer, and illumination is that the phase angle is mostly used for computing the brightness, so the so-called apparent magnitude, the illumination of an asteroid as seen from the Earth. And the illumination of an asteroid highly depends not only on the distance between Earth and the asteroid, or the also asteroid to the sun, but also on the phase angle. So that we will cover asteroids also in the future, where we will see very weird effects regarding the illumination of these objects. But yeah, I would just want to keep you curious so that you will follow it up and see what I mean. Now I computed all these values. Now let's make a cross check. Moon to sun. We have here the sun and the moon. Moon to Venus. So we have Venus as illumination. Observer 309 is the moon. Okay. So we computed it basically. And now we can say, okay, we would like to see when we have, let's call it photogenic seasons. Yeah. So when can we have a nice picture of the moon and the Venus together in the night sky, or in the morning or the evening, without the sun bothering us? Of course, we have to consider the location where we are and so on, but let's keep it simple again, and let's add a new column, and we call it, for example, photogenic. And for this, well, there are no scientific rules or so. We can define it by ourselves. First of all, we have to consider that, so we are applying now a function for all four angles, and we say, okay, if certain conditions are met, we say that that the setup is photogenic, and we can take our camera, go outside, and take a nice picture of the Earth, of not the Earth, of the Moon and Venus. Of course, considering the weather is good, right? So we say, okay, we want to have the value 1, which means we have a photogenic setup if certain conditions are met. Otherwise, it will be 0. And the question is, what could it be? So let's take first the 1 value. We have Earth, Sun, Venus to up. No, I need Venus to Sun angle, and we can say, okay, it has to be, let's say, larger 30 degrees. Of course, this is now artificially set. You can take any other values, of course, as well. It really, yeah, it should be realistic. If it's larger than 1 degree, this will probably fail. And then we can say, okay, and another value would be also the Moon to the Sun angle. That should also be, for example, larger 30 degrees. Oh, I just forgot some brackets here. And then, of course, Moon to Venus. Now you may ask why it's not enough. Shouldn't it be enough to have simply the these two values? Well, the Moon could be, let's say, on the left side of the Sun, and the Venus could be on the right side. This would fulfill both conditions, but they will be very far away, so separated. So we have to consider also the position, the angular distance between both objects as well. So we can take, we say x, and then we can take this value, and then we can say, okay, the angular distance has to be less than 10 degrees. Now this value depends a little bit on your camera, right? If you know, okay, I have a certain camera type with a certain lens, and my field of view is 15 degrees, for example, or 20, you can of course adjust the settings accordingly. Let's assume we have a lens that covers, like, let's say 12 degrees, and we don't want the Venus and Moon on the edges of our CMOS sensor. We want to have something, of course, some frame, some space in between. We say less than 10 degrees. And of course, I have to format it also correctly for GitHub. Else it's 0. Yeah, this is of course also important. Otherwise, we don't get anything. And we make the apply function along the axis. Now let's compute this, and no error was spawned, which should be good, I think. And okay, we have here now only zeros, but well, we have over 5,800 rows, but I think there are probably some unique values. Yeah, there are also ones in there. Now let's check how many are there. So we can now print some parameters, I would say. We could say the numbers of hours we are computing, which would be quite simple. We can just say, okay, it's basically the length of our data frame. This is like the number in hours, so I call it observation hours. This is like 5,833, and well, converted to observation days, we can this simply divide it by 24. Could also round this, but 240 days. So fits also here between October and June. And now the question is the number of photogenic hours or photogenic days. So let's call it just photogenic days, observation days. It's simply the length of the inner solar system DF and we have to consider only the photogenic values equal 1. And we have to divide it by 24. Oh, there is a mismatch. Now this happens. We have here this card. Okay, this is now awkward. Where is the problem? Inner this bracket here. Let me quickly check. So I did some mistake. This should work, right? Yeah, this works. Okay. So now log inner photogenic. Um, this is weird. Why is it an error? Probably you already see it and say there is the error. Just correct it. But somehow I don't see it now. Let me just do it from scratch somehow. I confused myself probably, right? Ah, I got it. I think I had the... Let me just do it again. Inner sources df photogenic equals 1. This is awkward, and this is really live. I mean, maybe it was a mistake from the other line. No, it was not. No, this is like really awkward. Inner solar sys df log inner solar sys df photogenic should be equal or should correspond to 1. I don't see there any problem. Now I have to check it. One moment, please. Now I'm a little bit now I'm getting a little bit nervous because I don't want to waste your time and my time with the bug. So let's let's continue, and I will check it later and upload it on GitHub. I don't know. Maybe I'm a little bit. I confused myself probably. I don't know why this doesn't work. It should work. Strange. Yeah, maybe I will see it later. It's really confusing me now. I mean, if I just take this one here, now I'm starting waste, and now I waste my time, right? And yours as well. This is, I mean, this should return some Boolean. Ah, there is still some issue there. Some I have this and that. I don't see it. I have literally no idea what's going on. Maybe I just copy paste it from here, and I just don't see it probably. It's interesting. Photogenic days. Now this is really, no, this is what happens, right? Let me try it, this one. I mean, it was like the brackets, right? Solsys df photogenic equals 1. Okay, I'm a little bit lost, but we will see. I think it's way, yeah, there is the mismatch here, and I cannot tell you what's going on now. Maybe you will probably write it in the comments that I'm not really competent to see it now. Well, this happens. Let's continue working with plotting, because we would like to plot also the our results. So how do the angular distance between Venus and Earth, Venus and the Moon change, the Moon and Sun, and so on. And also we would like to draw our photogenic seasons in there. Maybe when we have a plot, it's maybe a little bit easier. We import pyplot, of course, and we import the dates as well, because we have some UTC timestamps and we would like to print it in a human readable format. Now, the first thing, of course, as always, you know me, is we use the dark background. And yeah, okay, this works. Just have to be sure that I will not fail again. And now we have, of course, to create figure axis like PLT subplot, and yeah, set some figure size. I'm still thinking about the arrow. I don't know. I have to check it afterwards, and maybe add it to the video at the end of the session, so it's not getting too awkward. Inner solars is df, and we want to, of course, plot the UTC timestamp, so the time versus the angles. So the first angle we take is, for example, Earth, Moon, Earth, Venus to Sun. So the very first one we computed. And then we have to set a color. There's the comma. No, comma. And the color we set tab orange, for example, and then also a label where we say this is like, yeah, Venus Sun. Yeah, okay, we get an output. So we have some result, but let's consider this a little bit later. We also want to plot the others as well. So we make a simple copy paste. And the next one would be Moon to Sun. So we call it Moon Sun. And of course we should take another color like Sun. And then of course we have Moon to Venus. Moon to Venus. And there we take another color. Of course, we cannot take orange all the time. For example, red. And this is then Moon Venus. All right. Yeah, okay, let's ignore the plot for now. It works. We interpret it later on. We can now should also set some labels, like for example the X label, which is simply the UTC, so date in UTC, and of course a Y label as well. We set the Y label, and there we set angle in degrees, or phase angle. We can also call it, phase angle. Yeah, we can call it phase angle or angle, but let's keep it simply with the angle. And then we can also set some X limit or so to get rid of the values on the corners, on the edges here. So let's take xlim. We just say the minimum. It could also be the very first entry, and then of the UTC timestamp. And the second one, okay, now I have to be careful not to make a second mistake. That would be awkward again. Yeah, okay, so we have no empty spaces here in between. The Y values look nice, I would say. We could also say that we take from 0 to 180 degrees or so. But yeah, let's keep it like this. And then we can also improve a little bit the location here. We have now only the year and the month, and we don't see any ticks or so. It's a little bit difficult to read, I would say. So we could first of all add a grid, for example, only for the x-axis maybe, and x, and the line style. Line style is, for example, dashed, and then some alpha value as well. See how it looks like. Looks nice. So we have some separation here. So this is how we can a little bit improve our plots, and now we can also make some datetime formatting. And this is really like datetime formatting is always a pain. So of course I prepared a little bit where you can, for example, set the settings for the major locator. So this is what we imported above, where we can say month locator So let's see how it changes. And you see, oh, there's again an error. What did I do? Yeah, of course I have to call it. So yeah, there it is. It should actually change to the date format. No, it's the formatter, not the locator. I did a mistake. Yeah, this should be the formatter, not the locator. So if we now say x-axis set major formatter, then we have we can say matpl.de_dates, and then we say date formatter, and then we can say, for example, years, and then a human readable format of the month, which is simply called B. I think this should work. Yeah, now you see November, December, January, and so on. So it's maybe a little bit easier for us to read. And then we can, of course, set some minor locator, which is also maybe important, so that we see also the dates, right? So a-axis set minor locator, or format. No, it's a locator. And there we say matplotlib dot day locator. And then we should see, yeah, you see here the small ticks here, which indicate the dates. Now, this is, of course, a little bit small, but if you create a larger image, you will see. You can also add a grid for the minor, for the dates, but then it's getting a little bit overcrowded, I would say. Now, we have also to plot something else. Totally forgot our photogenic, let's say, seasons, where we can take photos. And for this purpose, we are iterating through our data frame. We could actually create subsessions or make a group by and stuff like this, but let's do it quick and dirty, where we simply go through the data and create vertical lines. I mean, this is not really the fanciest solution, but it works. Equals 1. Hopefully this will work. I mean, hopefully there will be no bracket arrow raised. And then we can say, okay, we would like to set vertical lines where the dates are. So we only extract the UTC timestamps where the photogenic setting is equals 1. And then we can create vertical lines. And for this, we, for example, make a new color like tab blue, a little bit similar with cyan. I don't know, maybe changing a little bit alpha 0.2. So let's see. Yeah, you see this is so fine that, yeah, it looks like bars actually. And now we see here our photogenic seasons, and we can talk a little bit about it in a moment, interpreting the data. Now let's first also add a legend. Fancy box, I like the fancy box. True. The location shouldn't bother us too much. So let's say, I don't know, upper right or upper left, upper right maybe. And also frame alpha equals 1. Let's see. Yep, there is our legend. So we are just covering some part of the plot that is not really interesting for us. And if you want to later upload the data or so, the plot, we can also rotate the X labels a little bit. So you see this looks now a little bit nicer. So yeah, it's just for the eyes, right? I mean, you can do it however you like, and then making a safe figure, but yeah, let's keep it like this. Okay, Now let's interpret the plot. What do we see? Now on the x-axis we see the dates, right? From October this year until June next year. And on the y-axis we see the angular distance between Venus and Sun, Moon and the Sun, and Moon and Venus. And as you can see, yeah, it changes all the time. Yeah, it's increasing, decreasing, increasing, decreasing, and so on. So for example, here at around 180 degrees, we have full moon, and around 0 degrees, we have new moon. And the same applies also between the difference between here, this angular distance between Moon and Venus corresponds a little bit, or is a little bit similar with has a similar pattern, but of course is related to this curve here, to the orange one, which indicates the angular distance between Venus and the Sun. Now we talked a little bit that around beginning of November, it appears that we can take a nice photo, and we verified it here. The our photogenic definition, yeah, that is defined here in this cell, indicates that we have a few days where we can take nice photos of the Moon and Venus together. So on this particular time frame. Now you can take the data frame and determine, of course, the dates. So it's probably something like the 8th of November or so. And that way, without now really using coordinate systems or so, simply by talking or thinking about phase angles and angular distances between the objects, we found out that yeah, we have some photogenic times where we can take pictures of these objects. And now you may recall that when I increased the month, so going to December, January, Venus was approaching the Sun again. So from us, the angular distance between Venus and Sun decreased at some point and then increased again, so that after February, yeah, or let's say beginning or mid of January, Venus becomes the morning star. So if you want to take a picture of Venus and Earth, you have to wake up quite early before the sun rises to take a picture. So now you have yeah, 2 remaining time slots, November and December. So take your camera, prepare it, and take some nice photos of this nice constellation. And I hope this helped you a little bit. You can take, again, of course, Stellarium. With Python, you can verify the time frames. And of course, it doesn't consider your location on our home planet. But I think you get the idea. In the future, these computations will get more complex. I hope you enjoyed it. Take care and see you next time. It's me, I'm back. I just checked the cell where the error was, and I was a little bit struggling and a little bit confused what's going on. And I found the mistake. It's, of course, in F strings, you have, of course, always be careful regarding the quotation marks. So I have here this double quotation mark for the F string, and I use double quotation marks also for the column. And this, of course, doesn't work. And this is a common mistake, and I have to say I do this all the time. Speaking of, humans learn from their mistakes, right? And now you see we have our results finally. So I can finally conclude in peace this this tutorial. So observation days 240, and around 9 days are, let's call them, photogenic days. This was the last add-on of this video. Apologize for this mistake, I would say, but I think this will happen again. This F-string types are sometimes a little bit confusing. Anyway, thank you very much. Take care and goodbye.